All right, welcome back. We are Game 2005. That's Game Physics in the fall 2021 semester at George Brown, and it's week 11, part 1 of our broadcast for the lecture series. So let's talk about where we were. We talked about a little bit of Intro to Unity in week 9, and I gave you a little bit of some physics stuff when it comes to energy of a system and conservation of motion. I think this is some good topics that you should still review. Some of you I don't think have yet. And then last week we talked about 2D collisions very briefly and got into how to create a Unity UI, a little bit of a Unity UI similar to what we're doing with we did with our IM GUI in SDL Engine, and as well as how to use a fly-through camera for your project so you can zoom around and take a look and inspect stuff in the scene, with an underlying motive of how do I use stuff in Unity? How do I add a script? How do I do stuff? Because this is kind of maybe for a lot of you, the second time you've touched Unity ever, right? Other people have more experience with Unity, so that might have been more of a review. But those 2 sessions that you had with me were just like, hey, how do I do stuff? You also had a session this week with Joss, and he talked about some kind of collision detection mechanism for as you're creating your physics with an F little engine that you're creating your own physics engine, how to collide with sphere collision, as well as how to collide with sphere plane. Those are the things that he talked about. He also talked about dot product and how that works to calculate the distance away from the plane, which I thought was neat, and how he was able to project the position from the center of the sphere to the radius onto the dot product, using dot product onto the normal of the plane to figure out the distance away from the plane at any point, which is kind of neat the way that was done. And I think that is required, because really you're doing a calculations where you're deciding the total distance away from the plane. Is it less than or equal to the radius of the sphere? And if it is, you have a collision. That's really the simple way of thinking about that. Okay. So that's why what he talked about in his lab. We're going to talk about, okay, fine, you've been able to collide. We can detect collisions on a 2D plane or even on the 3D plane. Well, what about just general response, best practices? Now, it doesn't matter whether it's 2D. We're also going to get into more details about 3D. But how do we do basic 2D response, all right? And we can extend the stuff we talk about today into 3D. That's what we're talking about today. If we have time, we'll do some Unity, but I doubt it. So let's talk about momentum and impulse. Again, when we think about conservation of energy, which is what where this leads into, we have this idea of when I have 2 or more particles in an isolated system, and when they interact, the total momentum of the system remains constant, which means that, remember, energy from the previous information we had before can neither be created or destroyed, only transferred. So this idea of transferring of energies is important, especially when we're simulating physics motions, right? So that's what we want to do. So what we're saying is the total momentum of an isolated system equals its initial momentum. Whatever it was initially is what it's ended up at the end. Total momentum. And momentum is kind of related to motion, right? So again, we can express momentum mathematically in a bunch of different ways, where, as an example, I have the momentum, which is represented by P. So P total is equal to P1 plus P2. This is a constant. Or we can also look at it as momentum initial, 1 plus momentum initial 2 is equal to momentum initial 1 final plus momentum initial 2 final. It's the same. It's a balance, right? So it kind of shows that, we can't change the momentum. It's just whatever it was is what it's going to be at the end. We're just transferring around. We're moving energies around more than anything else. This idea is what allows us to start thinking about this. And whenever 2 or more particles in an isolated system interact, the total momentum of a system remains constant. That idea is something that we're going to carry forward. All right, so again, in the conservation of momentum, there's nothing to say that the types of forces acting on the particles of the system itself. Forces are not really specified as conservative or non-conservative. Remember that when I use a force and I apply a force on a system, I impart energy. That's what I'm doing, right? So, and I don't also know if I'm using a constant push or an impulse. I don't have any idea of that when I'm talking about forces themselves, right? So here's an example. I've got this silly 60 kilogram archer. It's standing on a frictionless surface. He's on ice and fires a 0.03 kilogram arrow horizontally at 85 meters per second. Okay, again, going back into the physics idea, right? With what velocity does the archer move across the ice after firing the arrow? So here's some approaches. Can we use motion? No, because we have no information about velocities. Can we use Newton's second law? No, because we have no information about force, right? As an example. Can we use the energy approach, which is, potential energy, kinetic energy? No, but can we use momentum? Yes. So this is another tool in our toolbox, to give us some answers. Well, let's take a look at how we can use this. So again, conceptualize. The arrow is fired one way and the archer recoils in the opposite direction. So we're using Newton's third law. For every motion or for every action, there's an equal and opposite reaction. That's Newton's third law, right? So now we're going to categorize. We're going to use momentum, right? And we're going to say, let the system be the archer with the bow. That's particle 1. And the arrow be particle 2, or the second part of the system. It's not an isolated system in the y direction because the gravitational force and the normal force act upon it, the whole system. And there's no external forces in the x direction, right? So it's an isolated in terms of momentum in the x direction. Okay, so that's one thing we need to know. And again, we're just thinking about this. I don't need you to, we're not going to do any more formula in this course. There's not going to be another test, but I want you to conceptualize what we're doing here. So the total horizontal momentum then of the system before the arrow is fired is 0 because nothing in the system is moving, right? And therefore the total horizontal momentum of the system after the arrow is fired must also be 0, right? There's no momentum, right? So we choose the direction of the firing of the arrow as the positive x direction and identify the archer as particle 1 and the arrow as particle 2. So we know this information. We always write down the information that we know first. So mass 1 is 60 kilograms. That's the mass of the archer. Mass 2 is 0.03 kilograms. That's the mass of the arrow. And the velocity final that we're going to achieve with the arrow is 85 meters per second. And if we put the formula down where we have mass times velocity 1 final plus mass times velocity 2 final is equal to 0, they have to balance off, right? Then we can massage the equation where we want to know that velocity 1 final, right, is equal to mass 2 over mass 1. We divide the masses, so 0.03 kilograms over 60 kilograms. So the ratio of the mass of the arrow over the mass of the archer times the final velocity 2 to get the archer's velocity. Remember, velocity 1 final is the archer's recoil, right? That's what that stands for. Because anything to do with 1 relates to the archer, anything to do with 2 relates to the arrow. So the arrow fires in one direction, and then the archer is pushed back slightly in the opposite direction. Okay, due to the bow and the mass related. That's how you figure it out. And it has nothing to do with forces. It has nothing to do with what we've seen so far. It has everything to do with this idea of that momentum is conserved. All right. Okay, so if that's true, right, then we can go into more, other kinds of examples here. So linear momentum, if a particle or an object that can be modeled as a particle of mass m moving with velocity v is defined to be the product of the mass and velocity of the particle. So we can say that this is linear momentum, and it's usually a vector. Linear momentum is equal to mv, mass times velocity. Okay, there we go. Linear momentum is a vector quantity because it equals the product of two scalar quantities, right? Or a scalar quantity and a vector, and its direction is along the direction of the velocity vector, and it has dimensions that we see here in units are kilograms per meter squared. Okay, kilograms per meter squared. So how much kilograms per meter squared is my momentum, we can say. Okay, so why are we talking about momentum? This is going to give us a good response. The response is based on how much momentum, how much mass your objects have when they collide, right? Doesn't matter whether it's 2D or 3D. So if a particle is moving in some kind of arbitrary direction, right, where velocity has 3 components and your momentum is equal to mass times velocity, then it's equivalent to this idea where we can componentize or decouple each of the components of the momentum into different axes, x, y, and z. And so we can say that we can multiply the mass times velocity across the x-axis, velocity times the y-axis, and the z-axis, right, to kind of, decouple these things. And this is important, right? Using Newton's second law of motion, we can relate the linear momentum of a particle to the resultant force, where we can say something like the sum of all forces, as an example, is equal to mass times acceleration, where mass, we take mass times velocity over time. That would be acceleration, right? Velocity increase over time, change in velocity over time. When we look at that, we can massage everything to say the sum of all forces is equal to the change of momentum over time, right? How much momentum in a particular direction there's happening over time. And once we have that, we have this idea of, we're going to kind of develop an idea of impulse. What's the difference between impulse, or how does impulse, kind of work out in momentum? Okay, actually, we've seen that if we add an impulse force or an impulse, kind of to the, to an object, we're pushing it momentarily, as an example, within that moment. So the momentum of a system changes if a net force from the environment acts on the system. So if I have energy coming in from the outside or inside, then momentum changes. So we can say again that the sum of all forces, as an example, is equal to the change in momentum over time, right? If we solve for change the delta P, as an example, which is the change in momentum, it gives us this idea that the change in momentum is equal to the sum of all forces times over time, or over the change in time. So times time. So force times time is equal to change in momentum. And integrating this to find the change in momentum over some time interval, and the integral is called the impulse. If I integrate, if I go back the other way, right, where impulse of the force acting on an object over time is the change in time. Remember, whenever we think about change in time or delta time, we think about things like time final minus time initial. That's the change in time, right? So from its definition, we see that impulse itself is a vector quantity having a magnitude equal to the area under the force time curve as described below. So the force time curve is really the idea that over time, force is either constant or increasing, okay? So really what it does is it expresses this idea of this impulse momentum theorem, and the change in the momentum of a particle is equal to the impulse of the new force acting on the particle. So change in momentum is equal to the impulse. And this is equivalent to Newton's second law. So we can say that once we know this, that, it's equivalent to the second law, mass times acceleration, where force equals mass times acceleration, we can start kind of going back the other way and equating or relating impulse and momentum to mass and acceleration and forces, which is exactly what we need in terms of how things work from an energy perspective. So here is the force time graph. So you can see if I was going to look at this sum of all forces, as the time progresses, the amount of force in this particular graph increases, right? And then as it goes down, it decreases. This is an impulse, a pulse, right? Similar if we were looking at something like a heartbeat, right? This is kind of what it looks like. It's a beat of time. Over time, we have force that's exerted and it comes down. And the amount of impulse is this whole idea of area under the curve. Again, we use integration typically when we're getting that information. If we were going to do it by hand, we would use integrals, which is part of calculus. Okay, again, we're not doing calculus this semester, but it's good to know how we would do it. And one way of thinking about this when we're trying to figure out the area of under a curve, again, this is the mathy part that I just want you to think about, not necessarily remember or use, but just to think about it for now. If I was going to describe it, is if I was going to try and figure this out, typically what we would do is we break down the area under the curve in these small rectangles. That's how we originally did it. And the smaller rectangles that we can put in here, I'm just kind of drawing them haphazardly here. But the smaller rectangles, if we add up all these rectangles are easy to figure out because they're just length times width. And if I keep on adding all these rectangles around, I can add up all the rectangles to give us an approximation of the area under the curve. But integration does it a little better. It's a lot easier. And that's why we use calculus to figure this out, to figure out the impulse. right? We can kind of derive or integrate the impulse from the forces over time. So again, we can say impulse is equal to the sum of all forces over the change in time, right? And we can get something called the time average net force, which is the same impulse to a particle as the time varying force in it. So this is like another way of looking at this, where we're going to get a time average force. So the average amount of force over time, which is very similar to the impulse we're going to get in this one when we're trying to get the area under the curve. Okay, just giving you this example because these parts here are going to equate to, if you take this part here and you flip it around and you kind of put it in here inside the curve, it works to be the same. Okay, again, neat math. So in many cases then, if we get the average impulse, this idea of an impulse approximation, right, then we will assume that a couple things are true, right? The force that we're going to use is going to be called the impulsive force, right? And the particle is assumed to move very little during the collision. So I have a collision and I move, when they collide, right? As an example, there's not so much movement. And the idea is when we kind of transfer forces from one particle to the other, the impulsive force is an average, right? And where we see things like momentum initial and momentum final represent the momenta. If I say two momentums, then they're called momenta. That's the plural in Latin. Immediately before and after the collision. So we have some kind of momentum before and some kind of momentum after. Okay. Here's an example. Impulse momentum crash test example. In a particular crash test, a car of mass 1,500 kilograms, right, as an example, collides with a wall, as shown in figure 9.4. The initial and final velocities of the car are, so velocity initial, it's negative 15 meters per second along the x-axis. Remember the I with the little hat on top of it is the x-axis. That's representing that. Okay, so that's what happens. And then the final velocity, right, as an example, when it's hit, it goes in the opposite direction. Take a look at that, right? It's almost like a reflection in the opposite direction of 2.6 meters per second, so some kind of reflection. And if the collision lasts 0.150 seconds, so a fraction of a second, or 150 milliseconds, right? Find the impulse caused by the collision and the average net force exerted on the car. Now, one thing to know about collisions, remember we talked about two different kinds of collisions in the past. There are two different types. One of them is and we'll talk about it again, one of them is a elastic collision where it bounces and you have no loss of energy. And there's an inelastic collision. Those are the two general ways of thinking about this, right? So when we look at this car first, what would you say? Would you say that there's more of an elastic collision here or an inelastic collision? What are your thoughts? Just by thinking about the words, never mind about, what the physics says. Elastic or inelastic? What are your thoughts? Inelastic. Good, Neil. Here's why I agree with you, right? Because we have this crumple zone, right? If it was perfectly elastic, or even just elastic, not perfectly elastic, right? Then you wouldn't have the car crumpling, it would just bounce, right? And the car wouldn't deform in any way, right? And if we did that, there would be more forces coming back the other way, right? But what's actually happening is the car's compression that's happening here absorbs a lot of the recoil, right? Remember, for every action, there's an equal and opposite reaction. A car with a mass is hitting a hard point, a wall. The wall's not going to move, chances are, unless the car is really massive and goes through the wall. Chances are it's not going to go through the wall. It's going to crumple, and it's actually going to be reflected back away from the wall slightly at negative 2.6 meters per second across the x-axis, right? Why does this happen? Why is this not exactly elastic? Because of the crumple zone. And guys, we want the crumple zone. If we don't have the crumple zone, can you imagine the forces that are going to be exerted on the user on the way back out? The same amount of force, right, that's exerted against the wall, 15 meters per second, right? That's okay. Let's calculate that for a second as we think about this, right? So if I do 15 meters per second, right? And I multiply that by 60 seconds, and I multiply that by, 60 minutes, I have 54,000, meters, that's pretty fast, per hour, right? Divide that by 1,000, right? That's 54 kilometers per hour. We're going 54 kilometers per hour here, right? When we hit the wall, right? Can you imagine getting slammed with 54 kilometers coming back at you from the wall? You most likely would die. And the reason why this would be is because all of that energy would be reflected at you if this thing was perfectly elastic. Because it's inelastic, the wall and the car absorbs a lot of it. Look, most of it, right? If we think about how much is being absorbed because of this, the way the car works, if I take, 2.6 and, if I take 2.6 and divide it by 15, right, we're going to see that, only 17% approximately, or let's say 17.3% of the speed, right? And this translates into energy. The velocity, 17.3% of the velocity is reflected back from the wall, right? The rest, right, the other 83% of the velocity, and therefore the energy, the momentum, is absorbed, right? And where does the energy go? Remember, energy can either be created or destroyed. So where does the energy go? It goes into heat and sound and, which the crumpling noise and all that kind of stuff. And as well as the car, the original object, the rigid body, deforms. It's deformed, right? And that's great for real life. For us, for your assignments, there's going to be no deformation. Okay, I'm not expecting you guys to deform anything that you're colliding with. Okay, so that's something to understand when we're doing stuff. So again, we conceptualize the collision time is short. We only have a very short time for it to collide with. It's not like there's a continuous collision for very long. We can imagine the car being brought to rest very rapidly and then moving back in the opposite direction with a reduced speed, right? We categorize, assume the net force exerted on the car by the wall and friction with the ground is large compared with other forces, right? So that makes sense because think about the wall as the normal force. Whatever force is, almost all of it's coming back, would come back out again. Gravitational and normal forces are perpendicular, so do not affect the horizontal momentum. And we can apply impulse approximation in this case to figure out the total energy. The car's change in momentum is due to an impulse from the environment. Therefore, the non-isolated system, which is momentum model, can be applied. All right, so the momentum before and after the collision, between the car and the wall can be determined. We need to find the initial momentum, the final momentum, the impulse, and the average force, and we can kind of figure out once we get the average force how much force is being, coming back at us. Let's take a look. So again, momentum is equal to the change. The impulse vector is equal to the change in momentum. We can say that the change in momentum, or the delta P, is equal to P final minus P initial, right? And if we break this down, what P is, momentum itself is mv, right? Where we can say we're just further breaking it down. We're deriving it. So mvf, which is mass times velocity final minus mass times velocity initial. We can break this down. We can kind of factor out mass. We can say that the momentum is equal to mass times velocity final minus velocity initial. And once we have it in these terms, we have it in the terms that we've been given, right? We have velocity initial and velocity final, right? And we can kind of put those in, right? We can say that here's my mass, 1,500 kilograms. Here's the velocity final, 2.6 meters per second across the x-axis positive, minus a negative 15 meters across the x-axis negative, right, is equal to 2.6 times 10 to the fourth kilograms per meter squared. That is the amount of impulse that we have, okay? Once we find impulse, we can say that the sum of the average forces is equal to the impulse over the change in time. And once we've done that, we can look at it and say, well, because this is like finding Newton's second law, mass times acceleration, we know that it's going to be in newtons, right? So we can say that that is 2.64 times 10 to the fourth kilograms meters squared over the time, the change in time. So it's a very short collision time. 0.15 seconds or 150 milliseconds, which gives us a 1.76 times 10 to the 5th newtons across the x-axis. That is the total force, the sum of all forces, or the average force for that impulse. Whew. Right? So why are we talking about this? Because the idea here is that you understand, how forces are generated and what impulse means and what momentum means. Okay, those two things. So the term collision then represents an event during which two particles come close to each other and then interact by means of some kind of forces. Okay, and then the reaction forces are assumed to be much greater than any external forces present. Okay, this means that impulse approximation can be used. All right. And that's what we want to use. We want to use impulse approximation because it's far easier than using integration. Okay. So again, collisions, we talked about this, but let's talk about it in terms of sphere-sphere. Collisions may be a result of direct contact, and the impulsive forces may vary in time in complicated ways, and this force is internal to the system, and observe the variations in the active figure. So I have, example, a mass of mass 1 and mass 2. You can see that mass 2 is bigger than mass 1. And so mass 1 is going to kind of go in this direction from 2 to 1. That's the forces that are going to be applied. And mass 2 is going to go in this direction from 1 to 2. Now, because there's a less mass, M1 is less massive than M2. M2 is going to move a shorter distance. M1 is going to move a greater distance because of the greater mass of M2. That's typically how it works. But the total momentum is conserved, which means the total forces, if you will, that are in the system itself remain. Once we know that, we can use those kinds of collisions. Let's talk about those collisions again that we talked about earlier. We talked about elastic and inelastic collisions. In an elastic collision, momentum and kinetic energy are conserved, 100%. So that's what we're talking about in your assignments. I want you to think about your assignments that they're elastic collisions. Okay, so we're not going to crumple them. There's not going to be deformation. None of that stuff is happening, right? And in a perfectly elastic collisions occur on a microscopic level only. All right. In a macroscopic level, that means our size. Microscopic is like atoms and quarks. Macroscopic is people and objects, right? Only approximately elastic collisions occur. So not perfectly elastic. They're elastic, but they're not perfectly elastic. Why? Because some energy is lost because of deformation and sound and blah, blah. Okay? So these collisions are described by the isolated system model, and there must be no transformation of kinetic energy into other types of energy within the system. So we're not changing kinetic energy to potential energy. We're sticking with kinetic energy. Why? Because I'm transferring kinetic energy from one object to the other and from the other object back. Both objects are going to interact with each other, right? In an inelastic collision, that's the other type, right? Kinetic energy is not conserved. That was the thing we saw earlier, the car. This is an example of an inelastic collision. Why? Because we're crumpling and we're deforming a lot. And there's a lot less energy coming back out of the kinetic energy that's happening. As you can see, remember, kinetic energy is mass times velocity, mv, one half mv squared. That's what kinetic energy is. Well, you can clearly see that there's less velocity, so therefore kinetic energy is less. What happened to the other energy? It was absorbed, right? Or it was converted into sound or heat or smoke or other kinds of things. That's why it's an inelastic collision. So it's not conserved, and if the objects stick together after the collision, it is perfectly inelastic. So if I have two objects and they kind of stick together afterwards, right, as an example, and they're one after the collision, it's completely inelastic because there's no bounce. If things completely bounce away, that's another way of thinking about it. If I have a lot of bounce, then I have a perfectly elastic system. Well, more of an elastic system than an inelastic system. The idea of elastic and inelastic is going to help us with collision response. Doesn't matter whether it's 2D or 3D. Okay? So in an inelastic collision, some kinetic energy is lost, but the objects, they don't stick together, right? In elastic and perfectly inelastic collisions, there are limited cases, right? Because most actual collisions fall in between these two types. One thing to note is that momentum itself for the entire system is conserved in all collisions, even though kinetic energy may not be conserved. Okay? Momentum is always conserved because the energy itself, remember, energy cannot be created or destroyed. It's maintained. No matter what happens, we can't create energy, we can transfer energy. That's all we can do. All right, so in perfectly inelastic collisions, right, then what happens is if I have two objects, let's suppose, and they collide, then they bond together and they move together afterwards. So mass 1 and mass 2 come together, and somehow mass 2 continue going in the opposite direction. This is probably maybe not the right way of thinking about it, unless the velocity of mass 1 is very great, like way bigger than mass 2, then obviously they're going to bond together, go in the same direction as mass 1, okay? And the way it looks like this is velocity final is equal to mass 1, velocity 1 initial, plus mass 2, velocity 2 initial, over mass 1 plus mass 2. That is for inelastic collisions that bond together, and we get a final velocity where both masses are moving in the same direction. Okay, that's what happens there. So that's perfectly inelastic. So the only way that can happen, as an example, is if there's a lot of energy loss, right? A lot of kinetic energy loss. And why? Because the masses in real life would deform. Elastic collisions, on the other hand, what they do is, and this is more of what we're worried about, is when a mass comes, kind of towards another mass with a certain velocity, they reflect, okay? And we can say that, again, we know that momentum is not going to change because momentum initial is equal to momentum final. Think about this as the energy of a system. So we can kind of also say that kinetic energy initial is equal to kinetic energy final. We don't really lose kinetic energy in an elastic collision, all right, for the most part, right? So kinetic energy is conserved. We can say then that 1/2 m1 v1 squared plus 1/2 m2 v2 squared is equal to, that's initial, is equal to final, right? So when we add both those two things together, because remember kinetic energy is 1/2 mv squared, right? We can kind of take the initial kinetic energy and equals to the final kinetic energy. So, but the kinetic energy equation can be difficult to use. And with some algebraic manipulation, a different equation can be used. We can say that V1 initial minus V2 initial, right, is equal to V1 final plus V2 final. And that's just through algebraic manipulation, we come to this idea, okay? And this equation, along with conservation of momentum, where P initial is equal to P final, can be used to solve for two unknowns, right? It can be only used for a one-dimensional elastic collision between two objects. One-dimensional means we're moving across only one axis. Using this equation eliminates the need for using an equation with quadratic terms, right? Which reduces the need for, it makes the calculations easier. All right, so the following equations can be used for the final velocities in terms of the initial velocities because there are two equations and two unknowns. For example, V1 final, right? We can use this formula, and V2 final. So we have two velocities, and we have, kind of this information here. Notice that a lot of this is being duplicated. So we say V1 final is V1 initial, M1 minus M2 over M1 plus M2 times V1 initial. We can use these equations here, and we can sub in the information that we get together to solve from one equation into the second one. Okay, so this is kind of a key point. And why? Because once we have two equations and two unknowns, we can go down to, we can use a system of linear equations to figure them out. Okay, here's some special cases when it comes to elastic collisions. What happens when we have two collisions, as an examples, right? We have two collisions that are both, are two masses that are the exact same. M1 is equal to M2, right? What happens in that case when we have two masses that are the same? Okay. So if that's the case, right, if this is the case, then the particles exchange velocities. So they're the same exact size. Then if velocity V1 final is equal to V2 initial and V2 final is equal to V1 initial, we just exchange velocities. And that's a special case where the exact same stuff. So think about your spheres. Are the spheres in your assignment 3, are they the same mass? Chances are they are, which means they're going to exchange velocities. They're going to bounce and go in the opposite directions. Does that make sense? Yes, that's exactly how this should work. Okay? So this is approximately what one observes in a head-on billiard ball collision, which is kind of what you're doing. You kind of have these billiard balls, and because that's what you're kind of having in your little box of balls, as an example, right? They fall down and they strike each other, and you're going to get energy that's transferred between them. Okay. Now this is if we don't have gravity involved. Okay. Also something else. If particle 2 is initially at rest, and then here's the other case. So this is part of the same thing. If both are in motion, they exchange velocities. But if one of them is at rest initially, then the energy is transferred to the other one. In other words, then velocity 2 initial is 0, and then the previous equations become the other way around. Special case number 2. If m1, the first mass, is much greater than m2, okay? When a very heavy particle collides head-on with a very light one initially at rest, the heavy particle continues in a motion unaltered, and the light particle rebounds with a speed of about twice the initial speed of the heavy particle. So this is something that is another case. Again, I have a small ball, a very small ball, and a very large one. The other one, the first one keeps going in the same direction with the same speed, and the second one rebounds twice the speed that it was hitting the big ball. Okay, so now you might say this is kind of very similar to inelastic collisions, but they're not bonding. The two masses aren't kind of coming together here. When a very light particle collides head-on with a very heavy particle at rest, so this is where two particles are in motion, one that's very heavy, one that's very light, right? Here's another case where it's the same idea where one mass is much greater than the other one. A very light particle collides head-on with a very heavy one, initially at rest. The light particle has its velocity reversed. We can always think about the light particles hitting a wall, if you will. Okay, that's case 2. All right. So let's think about this stress reliever idea. Okay, imagine one ball coming in from the left and two balls exiting from the right. Is this possible? What do you think? So if I have one ball coming in here and hitting this group of balls here, right? Would two balls fly off from the right? Is that possible? What are your thoughts? So Patrick says the last one will be knocked. Sophia says, depends on the velocity of the left ball. It doesn't matter. If I have a really big velocity, what am I really doing? Remember, momentum is not going to change for the system. The amount of momentum final is going to be the momentum initial. If I've got a ball that's up here, right, as an example, and this is, removing gravity out of the equation for a second, so it's not going to slow down ever. Let's suppose that way, right? If I start this system going, I put energy into this ball here. This ball, because they're all the same size, transfers energy from one ball to the other ball until it hits this one. Okay, these balls, because this mass here, remember this one ball is hitting a larger mass, right? But they're not all together. So I'm transferring energy from one ball to the other ball because these things are all suspended, right? Then what happens with the final ball? It's going to transfer the energy to some degree minus some energy loss because of the sound it makes, the clacking sound. Clack, clack, clack. Every time it does that sound, it loses energy, right? Because it's got to go somewhere. It's created, we're putting energy in the system in terms of sound, right? So that's where the energy loss is happening, right? Also heat from friction, the balls hitting each other, right? And those kind of things, as well as air resistance, right? Air resistance is also going to play a factor, and gravity. Those are all the factors but we're still going to get one ball only that comes away. Let's take a look and see if this is possible. So due to the shortness of time, the impulse approximation can be used because we're only going to get a very quick hit, if you will. Okay? Categorize the system as isolated in terms of both momentum and energy. We also know that we're using elastic collisions because we don't have a lot of deformation here. Okay? So that's the first thing we have to look at. Next, check to see if momentum is conserved. It is. And check to see if kinetic energy is conserved. Okay, it's not. Why is it not? Well, therefore, the collision couldn't be elastic. If it was perfectly elastic, right? If it was perfectly elastic, then only one ball would come out. If we have two balls, that means kinetic energy is not conserved. Therefore, it couldn't be elastic. Finalize, having two balls exit was not possible if only one ball is released. Why? Because kinetic energy would not be conserved. It fails the test for making it, for having this, effect be possible. And this is kind of a thought experiment for you, right? Because, if we want to conserve both kinetic energy and momentum in a an elastic collision, if one of these checks fails, then we know we have a case where it doesn't make any sense. So here's the analysis. So this can happen where we have velocity that hits this ball, the energy gets transferred to the last ball, and the last ball comes up. But this can't happen because somehow, remember that we would need, like, we're going to move two masses with the same amount of mass. I have one mass, they're all the same amount of mass, let's suppose. They're all the same equal masses, right? And if I have kinetic energy, which is 1/2 mv squared, well, we know that kinetic energy final is equal to kinetic energy initial. We're not losing any kinetic energy, right? And the momentum, both momentum and kinetic energy must be conserved. Therefore, this can't ever happen because that means we would move twice the amount of mass with the same amount of velocity. It's impossible. All right, here's another one. I have something called a ballistic pendulum. All right. And the ballistic pendulum is an example where I fire a bullet and the bullet hits a block of wood, right? What happens to the bullet and the block? What happens? Well, we know a couple things, right? That the bullet gets embedded in the block. So therefore the block gets deformed, right? If the block gets deformed, we have a perfectly inelastic collision for both the block and the bullet, or one at the end. Okay, so again, observe the diagram. The projectile enters the pendulum, which swings up to some height where it momentarily stops and swings back down. It's an isolated system in terms of momentum for the projectile and block. It's perfectly inelastic because both of them bond together at the end. Momentum equation will have two unknowns. Use the conservation of energy from the pendulum to find the velocity just after the collision, and then you can find the speed of the bullet. Okay, so that's a different case than the other one. Here's another example, okay? A multi-flash photograph of a ballistic pendulum. Here's how it looks. So this is where you have a bullet, and the bullet or some kind of projectile bonds with the actual pendulum itself, and you can see what happens. It kind of goes out here, bonds, right? And then it comes right back at you again. All right, so we've been talking about kind of one-dimensional collisions in many ways, but what about two-dimensional collisions? And we're going to talk about 3D. We can always extend 2D to 3D, no problem. So again, the momentum is conserved in all directions, right? We can use subscripts for identifying the object, indicating initial and final values, and the velocity components. So subscripts like IX would be initial across the x-axis. IY would be initial across the y-axis, and so on, okay? And we can use these simple ideas where we have M1V1, that's momentum, plus M2V2 is equal to M1V1 final across the x-axis plus M2V2 final across the x-axis. We can use these ideas, right? Because momentum is conserved. Okay, two-dimensional collision example. Particle 1 is moving at a velocity of V1 initial. Here's the mass 1. and particle 2 is at rest. Okay? In the x direction, the initial momentum is m1v1 initial. And the y direction, the initial momentum is 0. But notice that they're not having a head-on collision. Only one part of the object, right, is hitting. In fact, we're hitting at a bit of an angle. Okay? So what happens is, after the collision, the momentum in the x direction is m1v1 final cos theta plus m2v2 final cos phi, where phi is the amount of angle away from the horizontal, and theta is the amount of angle away from the horizontal for the other object. Both objects are not quite aligned. One is above and one is below from the horizontal. And using these two different angles, whatever the difference is, right, we can figure out that it's going to combine those two things to go at an angle up here. After the collision, the momentum in the y direction, so that's the x direction, is m1v1 sine theta minus m2v2 final sine theta, right, as an example, or phi sine theta, right? And this is negative due to the component of the velocity being downward. That's only because of the way this thing was drawn, okay? The collision is elastic, and apply the kinetic energy equation, because if it's elastic, kinetic energy is conserved. And this is an example of a glancing collision, or what we like to say, a glancing blow. Okay, a glancing blow. So if they're glancing, right, how do we know they're glancing? Because they're not perfectly aligned, right? We have some kind of angle, right, some amount down from the original, and we can figure out the angle if we take kind of a standard point and we kind of equate, if we put a line between them, we can figure out how much of they're separated in terms of an angle from a particular axis. Okay? So we conceptualize, imagine the collision, predict the approximate directions of particles will move after the collision. In your mind, think about what they should do. Set up a coordinate system and define your velocity with respect to that system. It is usually convenient to have the x-axis coincide with one of the initial velocities, because that's easier than having two angles. And in your sketch of the coordinate system, draw and label all velocity vectors and include all the given information. Again, categorize. Is the system isolated? If so, categorize the collision as elastic, inelastic, or perfectly inelastic. Which one is it? Okay? Analyze. Write expressions for x and y components of the momentum of each object before and after the collision. Okay? Let's take a look at these things. So how would you do that? How would you, when we think about these things, is it elastic or inelastic? Well, we know it's elastic, okay? It can't be perfectly elastic because, again, that's only happening in microscopic levels, so it's just an elastic collision. We know that momentum is conserved, and so is kinetic energy, and therefore, once we know kinetic energy is conserved and momentum is conserved, we have two equations and two unknowns, and we can figure out, kind of the energy that's being transferred and in which directions. Here's another case. Okay, and this is kind of in line with what we just talked about, a two-dimensional collision example, all right? In this case, we have two cars coming from different axes, right? A 1,500 kilogram car travels east, this way, right? So it travels in this direction, this is east, right? And with 25 meters per second, and collides at an intersection with a 2,500 kilogram truck traveling north, right? This is north, this is the northerly direction, right? Right? At a speed of 20 meters per second. So faster, smaller car hitting a larger, slower truck, okay? That's what the situation is. Okay, so the question is, find the direction and magnitude of the velocity of the wreckage after the collision, assuming the vehicles stick together after the collision. Stick together, that is a key term there. Stick together means the collision is inelastic. They stick together, all right? They don't bounce apart. So it kind of shows you a situation where both masses are one over here, okay? So again, choose east to be positive x direction and north to be the positive y direction. Categorize, ignore friction. Model the vehicles as particles. Model the system as isolated in terms of momentum. The collision is perfectly inelastic because the vehicles stick together. This is the situation, right? So why wouldn't it be like this for our ball example in assignment 3? The balls bounce off each other. The vehicles collide and stick together. Different kind of situation. Okay. Analyze. Before the collision, the car has a total momentum in the x direction, and the truck has a total momentum in the y direction, because we've actually put them on axes here. In this case, we know that the change in momentum across the x-axis is 0, and the change in momentum across the y-axis is 0, because we know that momentum across the x-axis initial is momentum across the x-axis final. Same thing for this one. And we can categorize them with two different equations, 2 equations and 2 unknowns, right? And then what we want to do is we want to divide equation 2 by equation 1 to kind of create one equation that we can use. So we can say that sine over cosine, so the y momentum over the x momentum is equal to momentum tan theta. That's what it works out to be. And what we want to do is the arc tangent. We want to get the arc tangent to get the angle, right? Whenever we want to get the angle from forces or from a some kind of gradient, which is what's happening here, right? We want to get the arc tangent. So we plug in the values. So again, we know that 2,500 kilogram truck traveling north, that's on the y-axis, that's why we put it up here, times 20 meters per second. That is the values that we're getting, right? Now, the reason why we're not modifying it is because it's across the y-axis, so sine theta is irrelevant, right? Over cos theta, again, cos theta is at an angle of 0. Sine theta is at an angle of 90 degrees. Both equate to 1, right? So 1,500 kilograms times 25 meters per second. You take the first, values and divide it by the second values. And we take the arc tangent of this, which gives us an angle of 53.1 degrees final. That is the angle that the object is moving in. And then we know that the velocity final is the sum of the two masses, right, times the sine of the angle, right? So we sit there and say, okay, m2 times v2 initial is over m1 plus m2 sine theta. We kind of plug that formula in, and we say that 2,500 kilograms times 20 meters per second, right? That's the initial mass of the truck. And then over 1,500 kilograms plus 2,500 kilograms, we're adding the masses together, times sine of the angle we got, 53.1 degrees, is equal to a velocity of 15.6 meters per second at an angle of 53.1 degrees, positive to the top right corner of the coordinate system. So that's how you would find it. So again, perfectly inelastic collision calculation, and the angle and approach, the velocity, can easily be calculated. I'm just going to move on. There's an idea of something called the center of mass, and there's a special point in the system. All right, so and it moves as if all of the mass of the system is concentrated at one point. So the system, and this could be the system could be, when I think about a system, that could be the sphere or a group of spheres, as an example, or a car. Car could be a system as well. The center of mass is what we want to think about. We've been using the center of mass already because we've been trying to model a vehicle like a car or a ball or a cube or whatever as a particle. And that's why we've been able to do it, because we're looking at the center of its mass, as opposed to, if the object was kind of irregular in terms of how the mass was distributed. Here, we're always thinking about vehicles or stuff in our system, because we're making a very simplistic system for assignment 3, as if everything you're looking at has a center of mass, that everything is balanced, and that the rigid body is, the mass is distributed equally across the entire rigid body. Okay, as opposed to, example, in a car, you have a lot of the mass in where the engine is. There's a lot of mass there, right? More mass than everywhere else. Okay. Okay, center of mass and coordinates. The coordinates of the center of mass are x center of mass is equal to the sum of all masses initial across the x-axis over the total mass, right? And the same thing for the y component and the z component, which is the sum of all forces, times mass initial across the y-axis over the total mass. And then you can kind of figure out where the mass is going to be relative to the entire system. If we have mass 1 plus mass 2, and we want to find the center of mass of both objects, we can find that in the system itself. Okay. Notice here, mass 2 and mass 1. Imagine if I had something that was irregularly shaped. That's why we're talking about this, just as a concept. Imagine if I had a vehicle where I have a truck, and the front of a truck where the engine is. This is this part, right? There's the front of a truck, right? And we have the back of the truck, so let's say these are the wheels of the truck, as you can kind of imagine. This is the bed, the truck bed, right? And this is the engine. We can look at the front of the truck. Imagine if I'm drawing the truck. Here's wheels. It has wheels. It has an axle, right? As an example, this has an axle too. But you can see that the back of the area of mass in the back is definitely less than the amount of mass in the front. So you can see the center of mass will be something just behind the cab, if this was the cab of the vehicle, right? I'm just kind of conceptualizing with you to show you how this can work. But in this case, we're talking about two spheres. Okay. Sometimes we have an extended object, an irregular object, and this is nice to understand. But again, for our purposes, our objects are all going to be regular and rigid, not some kind of soft body mass. I'm skipping. How about center of gravity? Each small mass element of an extended object, again, has its gravitational force. We can also think about center of gravity, right? Center of gravity kind of looks at where the mass is, a single force acting on a point called the center of gravity. Center of gravity and center of mass are related. Again, not really something that we care about here in our example, but this is some great information for you guys to understand if we have some kind of an irregularly shaped object or system that looks like this. One thing that we want to look at sometimes is the center of mass of a rod, all right? And it really depends on how the rod is connected, right? If, for example, the rod is connected to a wall, or if the rod is freestanding, okay, depending on how the rod is. And we can see that depending on the length of the rod, right, we can kind of categorize where the center of mass is and what the rod will do based on if the center of mass is kind of towards the right or to one side of the rod itself. For example, in this case, if one part of the rod was smaller, tapered, or more massive than the other one, so this side is more massive than this one, then the center of mass would be towards the right, as an example. Okay, so again, I'm just putting that out there for your enrichment because we're not talking about objects like soft body objects or anything like that. But we want to kind of talk about it because you might see stuff like that, and it might give you some direction in terms of putting together a more complex physics system in the future. Okay, so I'm going to skip over here. When it comes to particles, momentum of a system with particles. And okay, so how about the motion of the center of mass? Again, we're talking about center of mass. We're going to keep going. How about rocket propulsion? Okay, this is interesting. So rocket propulsion is a special case, right? When ordinary vehicles are propelled, the driving force for the motion is friction, right? I use my tires to push the vehicle across, and then the car is modeled as a non-isolated system in terms of momentum, right? Because I'm adding momentum to the car with the force of friction. I'm pushing the tires are pushing the ground away, and it's propelling the car forward. That's what's happening, right? But the operation of a rocket depends on the law of conservation of linear momentum as applied to an isolated system. where the system is the rocket plus its ejected fuel. And this is where we talk about this, where rocket science is very challenging because of this loss of fuel, which means we have a loss of mass. So the center of mass of the system is changing. So this is kind of an interesting thing when it comes to rocket propulsion. So fuel is expelled, which means we have a delta mass, right, or a change in mass. And normally we've been always thinking about mass being the same, right? So the reason why rockets really work well is when the fuel is expelled, we have that, we're using Newton's third law, which is for every action, there's an opposite and equal reaction, right? But at the same time, the mass is dwindling, which means we're actually getting faster and faster, right? Why? Because as the rocket fuel is expelled, the mass continues to go down, and so we have more velocity over time. Very interesting. Again, outside the scope of what we're doing here in this course, but it's good to understand how this works. And you can use momentum in this particular case as well. I'm going to keep going. All right, good. So now we go into this idea of a collision response. Guys, any questions around velocity, mass, momentum, or impulse that we talked about so far? Right? Again, these are just concepts. Again, so that way you can understand what we're going to be talking about in the last slides. Okay, we're almost there. So again, both collision detection and collision response or resolution in some ways, they're big subjects, huge subjects. And it's really impossible to cover everything from a collision response in a single lesson. It's impossible. So that's why we break it down into 2D and 3D. However, what we're going to do is concentrate on some of the basics that are most commonly encountered, and specifically, we shall restrict our attention to collisions of particles with fixed walls, bouncing, and with other particles, which is what you're doing in your assignment 3. Let's talk about collision response. So topics covered in this chapter, or this part, include bouncing off horizontal or vertical walls, and by wall we mean any fixed flat surface, so a plane, that a particle can bounce off. We start with an example of a ball bouncing off a horizontal or vertical wall, and the collision resolution in this case is very simple. The effects of energy loss by bouncing of or wall friction can also be implemented in a straightforward way. That's one case. Case 2, bouncing off inclined walls. That's a much more difficult case. So Neil says, so we will use this to make the spheres collide and then fall away from each other in the assignment 3. I wasn't sure if we have to do that in assignment 3 or not. Well, it's definitely for assignment 3 because basically when you collide with assignment 3, right, with sphere-sphere collision, you want to respond to what's happening, okay? Bounce off inclined walls. The situation is more complicated if the wall is inclined, and you will see a general method to resolve collisions with walls of an inclination. In your case, right, your walls are not inclined, right? The box is just, kind of walls that are up and down, and then the plane, as an example, are walls there's a wall, the ground, which is basically, kind of across the one of the other axes. So again, really, if you think about this, the box, you're not doing inclined walls. You're doing this, horizontal and vertical walls. Okay, horizontal, the ground, vertical walls would be the walls of the box. Okay. Collisions between particles in 1D. When particles move along the line joining them, collisions are in one dimension and can be resolved in a very straightforward way. Collisions between particles in 2D. The final section discusses general method for resolving more complicated two-dimensional collisions between particles, and you can extend this into 3 dimensions, which we're going to do in a future lesson. How about bouncing off vertical or horizontal walls? So in the first thing, what we're going to look at is horizontal and vertical. We'll look at elastic and inelastic bouncing in turn, and again, bouncing in which the kinetic energy of the ball is or is not conserved. So if it is conserved, we can say that we have an elastic collision. If it's not conserved, we know that it's inelastic, okay? If the ball bounces elastically off a wall, its kinetic energy just after bouncing must equal its kinetic energy just before bouncing. In other words, kinetic energy is equal to 1/2 mv squared, and this implies that its velocity magnitude is unchanged by the collision. Okay, so we don't have any velocity change at all. It keeps going. So consider the first special case, right, in which the ball hits the wall perpendicularly with a velocity of v. In this case, the ball will bounce back at a right angle as well, right, and it'll bounce back the exact way in the negative v direction, right? So this is special case number one. So imagine if I have a ball and I'm shooting it or I'm projecting it in the exact, again, to the normal of a wall in 3D. It's going to bounce back right back at you, with the exact same angle. Okay, therefore, because its velocity magnitude is unchanged, the velocity just after bouncing will be minus v. Okay, this case is very easy to implement, right? You just reverse the velocity direction after the collision detection. However, there is something else to consider, which is the wall might be penetrating the wall slightly. So the ball and the wall penetrate. And why this happens is because of that idea that we talked about before, which is how much motion is involved for each frame. So example, if I was going to draw this out again, let's draw a bunch of squares to represent frames. Imagine where this here is a frame. So in this frame, it moves here. And then the frame before, right, it was, again, if we kind of imagine the same amount of motion, imagine the ball moves at the same amount of motion every single time. I'm just trying to make them as even as possible, right? They have the same velocity, every one of these boxes, right, approximately. Kind of draw them. So the ball was here, the ball was here, the ball was here, and then the next position was in through the wall, right? That can happen. And if that happens, if the ball penetrates through the wall like this, we need to reposition it back out. And we need to apply the bounce when it's repositioned, not when it's penetrating. Okay, so this is one thing that we're going to be looking for. First, we need to reposition the ball where at the exact moment it hit. Okay, that's something we need to detect. So something like this moment right here. We need to figure out when this happens, right? When it would have happened. We've already penetrated, right? But we want to position it here as if it would have happened here. And then we're going to bounce it or apply energy from this point onwards. Okay, we're not going to apply energy here. If I applied energy at this point, right, then we're going to get not as far back as it would have bounced, right, if it had hit the wall properly. Okay, does that make sense? Penetration, we need to reposition before we move up. I'm telling you this because this is something that you're going to note. You're going to be dependent on your detection algorithm, the way you use it, right, and how many frames. Obviously, the more frames we use, again, how we cut the, if we had 120 frames of collision, right? So if we can, the higher frame rate, the more accurate the collision is going to be. But that means that we can do more calculations per second. The more calculations per second we can do, the more slices of time that we're dividing, the motion of the ball. Therefore, in many ways, we're slowing it down, right? Relative to the amount of, if the speed is the same at the end, and we double the amount of frames, right, for the same speed, we're actually, in terms of our computer, we're actually slowing down how many pixels the ball will move every frame, relative to every frame, which makes it easier for us to get closer to a good collision compared to penetration like this. And that's why many cases, games that are played at 120 frames per second compared to 60 frames per second look a lot better. They look a lot smoother in terms of animation. They also work a lot smoother in terms of collision detection and response. Everything from lighting to, because remember, we use collision detection and response for lighting as well in many ways. All right, repositioning is necessary not just to avoid the visual effect of the ball penetrating into the wall, so visual weird thing happening, but also to avoid the potential problem of the ball getting stuck in the wall, which is also something that can happen, right? In the latter situation might arise if the reversed velocity of the ball is not sufficient for it to get out of the wall, especially if the velocity is also reduced to account for some kind of energy loss. And by the way, we're going to get into this idea of energy loss later on, where the wall itself, we're going to say, well, every time you hit the wall, you lose a little bit of energy. If we say that, then it's not a perfectly elastic collision. It's not an elastic collision at all, right? It's an inelastic collision. And the reason for this is because you're losing energy. If my kinetic energy is not preserved, if it's not maintained or conserved, right, then we have an inelastic collision. We have some energy loss. And the energy loss could be in the effect of the ball deforming a little bit. There's friction against the wall, friction in the air, noise, heat, all that kind of stuff can cause energy loss. In that case, the velocity of the ball would be reversed again on the next time step or frame and send it back into the wall. So again, going back to this, imagine if we didn't have this situation, but actually it's the other way around, right? So we even have a ball that's further in. So let's see if we can draw the shape just to really describe this idea, right? So if I was going to describe a ball, so this is the ball here, right? So this is the ball. Imagine here, that's okay. What if the ball was not like this, but actually it was like this? And you're inside the wall. Imagine the wall has a thickness, or it's a box in this case, right? If you're here in the next time step, guess what you're going to do? You're going to go this way. It's going to actually penetrate right through, and it's going to rebound in this direction, right? So if you're not careful, right, if you don't do it properly, then it's going to go this way, right? Right through, and at a very great velocity. It's, instead of it bouncing back this way, it's going to bounce this way. Yeah. Miguel says, eventually stop the object. Yeah, if you have inelastic collisions, eventually the objects will all come to rest. Okay. All right. And that means even if there wasn't any gravity involved, gravity also accounts for some of the energy loss in many ways. All right, so, okay, so the following code illustrates the steps for scenario shown in the previous figure. If a ball instance named ball and a wall object named wall, right, if they collide. Here's some examples. Here's collision detection. If ball X is greater than wall X, so the x-axis, minus the ball radius, very, very simple, right, then ball X is equal to wall X minus the ball radius. So first reposition the ball at the wall edge, and then reverse the ball's velocity, where the velocity of the ball, V, is, you're multiplying it by -1. All right? So in other words, you're reversing the velocity for the next time step. So really simple. Now this idea is something that we can carry forward in 3 dimensions. All right? Where once we penetrate the wall, what we want to do is we want to reposition the ball back out at the wall's normal, right? So where you're going against the wall, and then you're going to reverse the ball's velocity. Again, this special case is when the ball is directly hitting the wall across the normal. All right, so a very limited case. Okay, so perfect collision against the wall that's horizontal. Again, these simple 3 lines encapsulate the whole process: collision detection, the simple case, do I have penetration, repositioning, right, the wall at the point of collision, and then calculate the particle's new velocity just after the collision. Okay, so pretty straightforward. How about this example? So this is nice and simple, but what if the ball hits a wall at an oblique angle? And that's mostly what's going to happen, right? Instead of the right angle. In this case, implementing step 3, we need to consider the components of the velocity perpendicular and parallel to the wall separately. So in this case, in the case of a vertical wall, right, as an example, the perpendicular component is ball Vx, and the parallel component is ball Vy, this way, right? We need to reverse the perpendicular component. So x goes this way, right? So instead of x, okay, so let me just draw the perpendicular component. There's 2 components. This is the perpendicular component, and this is the vertical, let's try to draw that again. How come it didn't work last time? There is my drawing. This way, right? So this way is vertical. This is horizontal. This is vertical, right? So what happens is we don't change this part, right? So this part stays the same. We don't change this part. This part's still going to go up, right? But this part here is reversed. Okay, so this part here is reversed. It goes the other way, which means that if I'm going, then I want to, once I bounce, I need to reposition myself and then go this way. How come that did not work again? I think you get the picture though. That means it's going to go this way, okay? But this part is still going to go this way, which means you're going to go at an angle somewhere in the middle, which is kind of the opposite angle of where you're going this way. So this one's going to change, but depending on the amount of the y component, how much y component there is and how much x component there is, right, you're going to get that right, that angle, whatever that the resultant angle is going to be. You don't have to even figure this out. Just have to reverse the direction across the horizontal. Okay. Now this is not tricky. This is actually quite simple to do, right? And I'm bringing it up because this could be a solution, one possible solution in the way you come up with a bounce against the wall. So this technique of decomposing the velocity vector into normal perpendicular and parallel tangential components with respect to the wall seems entirely natural in this context, but its application is more general, right? So again, this is with elastic bouncing. If you need to be extra accurate, there's something else you need to worry about this time in relation to step 2, which is repositioning. In the previous code, we reposition the ball by moving it along the x direction so that it just touches the wall. But with the collision, when the collision is oblique, the ball's real position at the point of collision is along the line of collision. So the ball also needs to be moved a little along the y direction, okay? So again, going back up to this, you can see that we've repositioned it, but there's two components of repositioning, and that when we look at this in terms of x and y coordinate, so what this means is we have some amount that the wall of the ball that is penetrated this way, and some amount of the wall of the ball that is penetrated this way, right? So both ways, this way and this way, right? Because I've moved into the wall both this way and this way. I need to move some amount back and this amount over here. So some amount back this way and some amount that this way, so we can position the ball exactly where it would have collided. Okay, does that make sense? Because now you have an oblique angle. All right, let's go to that, right? So we'll devise a general method to do that in the next section. For the simple example, let's just adjust the x position only, and this should work fine and produce a smooth bouncing effect in most common situations, except perhaps if you have a really slow machine in which you might find the ball occasionally sticks to the wall, right? Slow machine means less frames per second. So we've talked about elastic bouncing, but what about inelastic bouncing? So inelastic bouncing is where we have no energy loss in kinetic energy for elastic bouncing, but in terms of inelastic bouncing, we have some energy loss. And it's easy to include the effect of loss of kinetic energy due to bouncing. All you have to do is multiply the velocity of the ball normal to the wall by some kind of factor less than 1. So again, guys, instead of figuring out all those things in computers, like things like, okay, let's add the friction, and let's add, let's subtract something like from a factor of 1, where 1 is perfectly elastic, right? So we normalize how much elasticity there is from 0 to 1, where 1 is perfectly elastic and 0 is perfectly inelastic, okay? If we have perfectly inelastic, what happens, right? Well, we have a situation, if we had a perfectly inelastic ball, and if it was colliding against a wall, let's suppose this was the box, right? And if we had a perfectly inelastic collision with the wall, let's maybe draw it slightly differently like this, then what we'd have is the ball and the wall would stick together like this and just stick there, perfectly inelastic, right? So zero bounce completely, it just stops. So perfectly inelastic collision, where the collision just stops. You're not allowed to go forward. It doesn't go through the wall, it just gets repositioned. Okay? Perfectly elastic means that it would bounce, right? Bounce with all of the kinetic energy. So that means we can normalize that value. We can create some kind of normalized value. And usually we use, these special numbers in programming, let's say between 0 and 1, 0 to 1, where 0 is perfectly inelastic and 1 is perfectly elastic. Or we can also think about this as, 0% and 100%, where 1 is 100% and 0 is 0%, this idea, right? How much percentage loss? If I only lose 1%, that means every time I hit the wall, it's 99% purely elastic, right? We keep on losing numbers. So using one factor is much easier than if we try to figure out all the things that are affecting us in gameplay. And for the most part, it's good enough, is what we're saying, okay? So again, in real world collisions, there's loss of kinetic energy, but in games, who cares about the real world stuff? We want to emulate what it would be like to be in the real world, right? So we're saying that it is easy to include some kind of factor that's less than 1 and reversing it. So here's an example, right? So ball of, velocity, we're reversing the velocity. It's a perfectly elastic collision, right? That's great. But if it's inelastic, we can multiply it by some kind of velocity loss or energy loss factor, all right, that we want to multiply instead of purely -1. So instead of hard coding it to -1, we can use some kind of factor when we're multiplying the velocity. It's still reversing, but we're reducing the amount of energy that's kind of going out, okay? This idea is so simple to implement, guys. We just have to come up with a reasonable amount of loss, whatever that reasonable amount of loss is. A value of 1, again, corresponds to perfectly elastic, while a value of 0 corresponds to completely inelastic, and which the ball just sticks to the wall. You can experiment with different values. I recommend doing that with your IM GUI or something like that in Unity. Okay. Similarly, you can model the effect of wall friction in a simple way by multiplying the tangential velocity, right, of the ball itself as well. So two things. Notice that this is energy loss of bouncing. So in other words, the bounce itself, which is across the horizontal, right, across the x-axis, that's like where the ball actually squishes. Remember, when we think about the ball itself, instead of the ball being perfectly elastic and maintaining its shape, we have a little bit of deformation in real life, where the ball actually doesn't stay completely. So imagine if there's a wall here. Let's look at a wall that looks like this. Here's the wall, right? And we have a ball that hits the wall. Well, the ball, that when it hits the wall, isn't going to be perfectly shaped properly. It might flatten out a little bit. It might do something like this, right? Where the ball hits and compresses, right? And it kind of creates almost like a springy force, right? For it to go where it's supposed to go. So this compression is what we're talking about here across the x-axis, right? This deformation. But of course, this is only if the ball is traveling perpendicular to the wall. So if it's going in this direction, perfectly perpendicular. If it's at some weird angle like this, then obviously it wouldn't just deform across one angle. It would deform across the oblique. So it would be a different deformation that's happening, right? And so we can account for this, right? If we really want to be super accurate. So one thing it talks about is two factors, factor across the x-axis and factor across the y-axis in terms of wall friction. Friction means how much the wall will slow the ball down when it hits, because friction means I'm sliding against the wall. So not just a bounce, but a slide, right? That's tangential force. And notice again that there is the absence of a minus sign in this case, because friction reduces but did not reverse the tangential velocity, right? So tangential velocity is reversed in terms of a bounce, but wall friction just reduces. Okay, so you can actually have more accurate results this way. Okay, any questions around bouncing off horizontal or vertical walls? Horizontal vertical walls is your case, the case for assignment 3. Everything is horizontal or vertical, if you think about it. Okay. What about if you're bouncing off incline walls? Okay, now that's a different problem to solve. So this is significantly more complex than if the ball bounces in an inclined surface of some kind, right? So again, if it's inclined at some angle to the horizontal or vertical axis, the world axis we're talking about, the same steps apply, but they are now a bit more complex to implement. So different approaches can be taken here. A common approach is to perform a coordinate rotation to make the wall horizontal and do the bouncing and then rotate everything back. Right? So treat it as if everything is horizontal. That's kind of a neat way of doing it. For our purposes, because we're using vectors, we have devised an alternative method that exploits the vector formulation and avoids the 2 coordinate rotations. But this is definitely a way of doing it. Coordinate rotation is a way of bouncing off incline walls. So collision detection is much less straightforward with bouncing off an incline wall as well, because it is not a simple case of checking the X and Y position of the ball in relation to the wall, but thinking in terms of vectors helps a lot. Let's take a look at the following figure, which allows a particle approaching a collision with a wall. There are basically 2 conditions that must be met for a collision to occur. 1, perpendicular distance of the particle from the wall must be smaller than its radius. The perpendicular distance is what Joss talked to you guys about in your lab. Okay? Is it true? Did he talk about perpendicular distance? And remember, he asked you guys in the lab, he said, hey, guys, what is dot product, right? And dot product we calculate by taking the, the normal. So let's say this is the normal. I'm just roughly kind of putting this together. Let's say this is the normal. And we take, kind of the center of the ball, the center point. We project it onto the normal, as well as the bottom of the ball, which is the radius, right? And once we have this onto the normal, we have this interesting line that goes from here to here. This is the shadow that he talked about. This shadow, all right, that we're having right here, we can take this line here and we can calculate the distance from here to here. So that's the shadow. This is where the ball is at the edge right here. And then we can calculate this distance, the distance from, we'll use the purple line here, the distance from here to the wall. All right, this distance from here to the wall, D, is the distance that we need to know, and that's found out by using dot product. All right, we project, we're doing vector projection, all right, and that's what we're doing here. So this is the distance D, and this here is the projection. Okay, so we take the projection idea, and what we're doing is we're saying, okay, we're projecting the radius and, the center and the radius, those 2 points, we're projecting them on the normal. We're drawing a line, and we're saying from that line segment, from the end of that line segment, or where the radius hits the normal, to where the wall starts, as an example, that's the distance, that's the separation. And that's true from anywhere across that wall, or plane, if you will. That's what he talked about. If you haven't had a chance to go to the lab, please take a look at the video. I think it's pretty good what he talked about. All right, so the perpendicular distance from the particle, from the edge of the particle to the wall, if it's smaller than its radius, then we know it's collided. It's pretty simple calculation. Wall, sphere and wall collision, or sphere plane collision. Okay. But in the following diagram, P1 and P2 are the position vectors of the endpoints, right? P1 and P2, okay? And so the endpoints being, O of the the points of the wall with respect to the origin. Let's suppose this is the origin, the world origin, 0, 0, right? And W is a vector from the endpoint marked A with position vector P1. So here's the endpoint of the wall, A, and here's the endpoint of the other part of the wall, B, from A to B, right? And then P1 is from the origin to one endpoint, and P2 is from the origin to the second endpoint. So these are vectors, right? We kind of get these vectors in two-dimensional space, in this case, or in three-dimensional space. Okay, so we kind of have the magnitude. This number here, if you think about what those things are, that's magnitude. So if I was going to draw this out, P2 is really the magnitude, right, between the origin and B1, and B, this P2. P2 is actually B's magnitude. P1 is actually A's magnitude, right? And we can also find the magnitude of the circle, here in this case, or the sphere, from the origin to where it's at. Once we know those three magnitudes, we have some information, okay? We also have information, we can also calculate the vector between the center of the ball and A and the center of the ball and B. We have all other vectors here as well as the center of the ball and Q, which is Q being the shortest point from where the ball is to the wall. Okay? And so it's interesting that they break it down this way. Again, this is another way of thinking about it with this incline wall. Hopefully you're with me still. Okay. In terms of these vectors, the first condition is simply the following. Where r is the radius of the ball, then the distance, if the distance is less than the radius, then we have a collision. That's pretty simple. The second condition can be stated in terms of the projections, QA and QB, of the vectors B1 and B2 in the direction of the wall vector W. So again, we're making that projection happen. The wall vector W, we're projecting these two things down here and this one down in here. So where does this project? If I do a projection, remember anytime we do a projection relative to some other plane, in this case, let's say this is the hyperplane. So if I do a projection, right, from here, from this point here, down here, I'm going to project it down to this point, right? If this is the relative to the normal, right? And again, I'm going to project this point right down to the wall relative to the normal. Okay. Creating almost a shadow, if you will, right? Again, projections. So if the length of both of these projections is less than the length of W, it means that the ball is between the endpoints of the wall. Okay, so the length of these two projections, if the length of these two projections is less than the length of the wall, we know that the ball is somewhere between these two endpoints, somewhere. That's what it means. Okay? Otherwise, if either projection exceeds the length of the wall, the ball must be outside of that range and won't hit the wall at all. In other words, if this thing here, right, if the projection is somewhere over here on the outside of the wall or over here, right, the wall down to the closest point, right, then we know that the ball is over here or over here. That's what this is saying. Because we need to figure that out too. What if you have a plane, but you're on one side of the plane or the other side of the plane, but you're not actually towards the plane? All right, that's a problem we need to solve. So it remains now to work out the length of the projections and the distance d from the unknown vectors P1 and P2, from the known, I mean, and P. By using the rules of vector addition, we get the following. The wall is P2 minus P1. So the length of the wall is P2, so the magnitude of the origin to B, and the magnitude of the origin to A, the endpoints of the line, the line segment, right? That's what that is. We know that the length, right, the wall itself, the length or the vector, if you will, we're getting a magnitude. P2 minus P1, we're going to get, that's what W is, right? By similar reasoning, the vectors b1 and b2 are given by these equations. b1 is equal to p1 minus p, and b2 is equal to p2 minus p. b1 is p1 minus p. So p1 minus p is b1, right? We can get, that's how we got that vector. And b2 is p2 minus p. Again, if we do those two calculations, we get that vector. So this vector and this vector and this vector. Right? Pretty nice, eh? So far. It's all vector calculations. All right. So, and then in pseudocode, we can write something that looks like this. Ball to wall 1 is equal to wall P1 subtract. We can say subtract ball and in 2D position, whatever that ball is, right? And ball to wall 2, or B2, is wall P2 subtract ball, or we can use vector 2s in Unity. It's pretty simple. Then the projection of the vectors ball to wall 1 and ball to wall 2 into W is given by projection 1, ball to wall projection is the wall vector. We pass in the wall vector itself. And then ball to wall 2 projection onto the wall vector itself versus projection 1 and projection 2. Again, imagine we have when we talk about pseudocode, we're imagining that we have a subtract function, right? We're imagining we have a projection function, right? Remember, we can make our own projection function by kind of making use of dot product, okay? Okay, so once we figure all this out, we can then figure out the distance, ball to wall 1 subtract the ball to wall 1 projection across the wall vector, right? That's what we want to do. And once we figure this out, we know the distance, and if the distance is less than the radius, we have a collision. And we can know how much of a collision too, because we can subtract them. Okay, and let's just get rid of those little lines and our annotations. There we go. So again, once we've done that, we figured out how to collide, but now we need to reposition. And the way we want to reposition is exactly the same. If we have an angle, what we want to do is if the object, let's say the particle, is hitting the wall and it penetrates, what we want to do is we want to move it back to the point where before it penetrated. And we want to do both the penetration across the normal as well as in this direction. So we move both back to this point. And again, we use projection to get that done. More complex, kind of something we have to think about. Okay, we're almost done, guys. I don't want to keep you too much longer, but this idea is what we're talking about. So again, things that we've learned, summary so far. We know that collision detection is not just enough. Step 2 after collision detection is repositioning. Step 3 is reflection, okay? And usually 100% elastic or some factor that is inelastic, some reducing factor, right? Usually across multiple axes. 1 for the reflection, the bounce, and 2 for the friction. Okay, the friction with respect to the wall. All right. So this just talks about when we reposition, we want to think about the direction, as an example, and we use trigonometry to do this, right? And when we can say that when we want to displace the particle is carried back along that same angle of approach. Think about this as the angle of attack. I have an angle of attack, and I want to move it back across this line of approach or angle of attack, back to where it would have collided, where the difference between where it penetrated compared to where it should have stopped. We move it back to where it should have stopped, which is against the wall. Okay, and then from there we reflect, right? We reflect at this particular point in time, not here. More challenging to do, but they talk about it here in the code, and they give you some examples of how that would be. Calculating the new velocity is going to be based on a velocity vector, and it's based on the angle of approach. Okay, I'm just going to skip because I want to talk about this. So here's an example of a ball with some pseudocode. a ball bouncing off an incline wall, and I've given some code here that you can use in your examples to bounce off any wall itself. Again, what's the vector along the wall, right? You want to find the direction around the wall direction itself. Then you want to find ball P1 and P2, which are just endpoints of the wall itself. And then you want to do projections of the above vectors onto the wall vector. You want to calculate the perpendicular distance vector from the object to the wall. And then what you want to do is do some collision detection. This is the collision detection piece with built-in repositioning, which is what's happening here. Notice we're using dot product here. All right, so this should help, kind of figure out what you would do. Just think about subtraction. If I do subtraction is like vector 2 minus vector 1. And it continues. All right, so that is, colliding at an angle, right? How about handling collisions between particles when approaching a direction of the particles along one direction, or 1D collision? How do we do that? And why do we even study it? It's because methods and formulas that hold in this special case can be readily extended to the more general case where the particles may collide at any angle. In fact, we will do that in the next section. So again, think about this. Steps for handling 1D particle collision are the following: collision detection, repositioning the particles at the moment of collision, and calculating the new velocities just after the collision. That's what we talked about. That's almost like a summary of what we just talked about all in the second half of this lecture, right? So in the case of spherical particles or circular in 2D, the first step, collision detection, is very simple. As discussed, right? You just see whether the distance d between the centers of the two particles is less than the sum of the radii. That's what we talked about last week, all right? And where d is calculated from the position coordinates, x1 and y1, and x2 and y2, using Pythagorean theorem. So collision between two particles, not wall and particle. Okay, that's what we're talking about here. And in 2D, it would be the distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. Again, you don't want to do this. Maybe you want to use squared distance, and then, kind of the squares, add the addition of these two squares, because it's less computationally expensive per frame than the square root. And then what we want to do, if we have two particles, is we just reposition the particles themselves based on information about their velocities and masses. Okay, let's assume that both particles are equal mass. Remember that idea? Then they both swap velocities. This swapping of velocities happens. Okay, but we need to reposition them first in the place where they would have collided based on where they were before. So again, the complication is in general that both particles may be moving, so both need to be moved back to their position at the actual point of contact. But how do we know how much to move each particle? Let's begin by considering the case where the two particles are moving toward each other, as shown in the figure up here. This is the first case. Well, the amount of overlap L, this overlap here, right, is given by the following, where R1 and R2 are the radii of the two particles, right? This radius and this radius, R1 and R2, right? And D is the distance between their centers from here to here, okay? So we can say that the length, or the overlap, right, is equal to the R1 plus R2 minus the distance. That's how much overlap. That's a number, right? Scalar, right? Let's set S1 and S2 to be the magnitudes of the displacements by which the particles must be moved back in opposite directions so that they are just touching. These displacements must add up to the given overlap distance of L, right? So S1, so the displacement of the first particle plus the displacement of the second particle, how we move them back, must be equal to the total overlap. And this gives one equation relating S1 and S2 in terms of known variable L. In order to be able to work out S1 and S2, we need a second equation connecting them, right? We come up with such an equation. We're recalling that in a small amount of time interval t, the displacement is equal to u times t, and the second displacement is equal to u2 times t, where u1 and u2 are the velocities of the respective particles just before the collision. and t is the delta time, right, as an example. And that's just using the fact that displacement is equal to velocity times time. So that means that if this velocity, whatever this velocity is times time, that will be the total displacement of the first one, right? That's how much I have to position it back. And plus the displacement of the second one, that's how much I have to displace this one back. So if this one was moving faster, I have to move this back more. If this one was moving slower, I have to move this back less. But the total has to be equal to the amount of overlap for us to get perfectly repositioned. Okay? All right. And then we can figure out something that looks like this. We can divide the first by the second, and we can kind of move things around, right? Some algebraic manipulation. And then it is now a matter of simple algebra to solve for S1 and S2 to give this. S1 is equal to the velocity of 1 over the velocity 1 plus the velocity 2 times the total overlap. That is S1. And S2 would be velocity 2 over velocity 1 plus velocity 2, so the ratio, right, times the amount of overlap. That's the amount of displacement for the particle number 2. Once we have these displacements, that's the total distance we need to move them back across that one dimension. Guys, this is the key that we need when it comes to all particles that are moving in all dimensions, once we have this idea. Okay? So that's great, but what if we have the other situation in which the two particles are moving in the same direction rather than toward each other, all right? And with the one behind moving faster so that a collision actually happens as shown in this figure. So both moving are in the same direction, right? Where U1, which is the velocity of particle 1, is much greater than the velocity of particle 2. Again, we have this overlap, but now we have a different case. So now we can figure out that S1, the total kind of displacement where we want to move S1 back, is equal to U1, which is the velocity of particle 1, the negative velocity of particle 1 over the absolute value, that's what these lines mean, of velocity 1 minus velocity 2 times the overlap distance. And the same goes for the displacement of particle 2. Does that make sense? And notice that the displacement of particle 1 and particle 2 are in the same direction, this way. They would have collided earlier, somewhere over here. All right, so that is repositioning particles based on moving particles and in 1D. What about in 2D? Well, now we get to be more complex, okay? And these are things you should consider, right? The way to handle such collisions is to resort to a trick similar to that used for the ball colliding with a wall. At the point of collision, when the particles are just touching, resolve the velocity of each particle into a normal component along the line joining them and a tangential component perpendicular to that line. So this is the line joining them, right? And then a tangential component perpendicular to that line. So this is two velocities. Here's the velocity vector for particle 1. Here's the velocity vector for particle 2. They're going to glance off each other, right? And imagine that they're like two walls or two balls hitting two different walls, where each ball is kind of the wall for the other ball, kind of. That's kind of what it is, right? So imagine at that instant of collision that this ball, if we consider this as ball number 1, right, is the wall for ball number 2. And this ball for ball number 1 is the wall, right? So it's kind of a trick that is being used. So imagine that this is the wall and this is the other wall. Depending on what you're looking at, if the ball is colliding with the wall, and we can actually put a wall, kind of a surface between them, something that looks like this, we can say that that point of collision is where this ball would bounce, right? So we bounce against this place. Here's the wall. Then we're going to bounce the same. Imagine if we have an angle of attack. Let me just draw that again. We have an angle of attack here, right? Here's the angle of attack. Well, we're going to bounce at the opposite angle. So we're going to kind of, from this position here, we're going to bounce at this angle, right? And for this position here, we're going to bounce at this angle, right? Whatever the opposite angle is of the attack. right? So this ball is going to bounce this way, this ball is going to bounce this way, but they need to be repositioned back along this vector here. We're going to make a line between the two centers. And that line across the two centers is going to be where we're going to use to kind of make them go back this way, right? Reposition them this way and reposition them just like if they're hitting a wall, okay? So that's the trick. And the idea is that just as in a collision with a wall, only the normal velocity components are affected by the collision. The tangential components remain the same after the collision, provided it's frictionless. If it's not frictionless, then we can add some reduction in speed due to friction of each ball, right? If it's inelastic somehow. Okay? So again, here are the steps for 2D particles colliding that we have. First, detect the collision. We know there's an overlap. Decompose the initial velocities in normal and tangential components. Reposition the particles at the moment of collision. Calculate the new normal velocities just after the collision, and then add the new normal velocity components back to the tangential components to move them in the right direction. Okay? And again, what you want to talk about is here's a 2D check collision function. I've just given you over 2 slides where I have if the distance, the length, is less than the radius of the two balls combined, we know that there's an overlap. By the way, this works for spheres as well, right? Just in 3 dimensions, right? The distance between the two vectors, right? You just subtract the 2 spheres, you add the 2 spheres radii, and if it's true, you have a collision. So we know there's a collision in here, in this part, right? That's the first piece. And the second one is we're going to say, okay, cool. Then first part is the normal velocity vectors just before the impact. So I want to get the normal for ball 1 and the normal for ball 2, normal velocities. And I also want the tangential vectors for just before the impact, right? So again, the tangential velocity for ball 1 and the tangential velocity for ball 2, right? Because I have those 2 vectors, right? And then I move the particles so that they just touch. And I say that the L, which is the overlap, is equal to the ball radius 1 plus ball radius 2 minus the distance, right? So that's how much overlap there is. Once I know the overlap, then what I want to do is I want to subtract the amount. That's the relative velocity of both balls. And then I want to change the position of both balls based on the amount that they've moved through the wall. Both on, that's the repositioning piece. And then once I reposition, now we're going to add in the velocities based on where they touched. Okay, this is the velocity. So normal velocity components after the impact, and this is the normal velocity vectors after the collision, right? And this is the final velocity vectors after the collision. So if you follow this idea, you're going to get kind of 2 objects or 2 balls that are colliding in space, right? And by the way, those kind of calculations is something that Joss is going to be working with you on in the next lab, right? Because so far we've talked about the first case where you have a plane and you have a wall collision, right? And that idea is the plane ball collision is something that you've already covered. 3D particle collision is happening next week, yeah. That's what the plan is. And that's why I couldn't do a Unity tech demo today, because there's so much theory to cover in this one, okay? 3D collisions, we may have more time, and 3D collision response is building on what we talked about today, right? So again, by next week, that's when assignment 3 is due, next week, but you'll have enough from Joss's lab in order for you to complete assignment 3. Yeah, it's a lot to cover, for sure. All right, I'm sorry I went over time, guys. Any questions before we go for the day? This is all the theory that you'd probably require in order for you to, again, be able to understand what's happening, not just, kind of do it in Unity. Sam says, I had a question about our lab 6 to 12. Is it all right to have a single repo updated for each lab, or should I have a new one for each piece? Talk to Joss, Samuel, because he's the one that's going to be marking them. Okay? He's the one to do it. Okay, any other questions? Josh said, just have a clear commit labeled for each one in the same repo. Cool. I'm fine with that too. All right, guys. Thank you so much. Take care. And hopefully that helped kind of clear some stuff out. I know there's a lot of theory around collision detection and response, but one of the things that we wanted to talk about is this idea of momentum and impulse. And we also covered the idea of collision detection and repositioning, and then response, which is kind of the three pieces you need for any kind of proper collision detection system. All right, thanks, guys. Take care. I'll end the stream here.